Welcome back to Dave Does Math from Home. Today we're working on part 2 of section 8.4. In the first section we came up with this technique for substituting signs in for x's when things look sort of vaguely like this. So by the time we were done with it, the integral had just simplified into the integral of 1 d theta. It was very nice. And we turned that into a formula. It was good. The question of this video is, what do we do if there are additional x's involved? At the very beginning of the last video I said if there's one x here, then we can use substitution, regular old-fashioned inside outside other substitution. If there's an x squared here, that's not an option. If there's an x squared here, we have to do the trig substitution like normal and then deal with whatever comes out of it because of that x squared piece. So we're just going to go through it, see what happens. Stay with me. X equals sine theta is the traditional substitution because I have a 1 here and I don't need to account for any other numbers. If this was like a 4 or a 9 or a 16, we would have to put a number here to account for that so that the squared number matches this. Dx then is the cosine of theta d theta, and when I substitute I get x squared is sine squared theta on top. Dx is cosine theta d theta, and the denominator is the square root of 1 minus sine squared theta. At this point, I'm going to skip kind of a lot of steps because we've seen this before. We know that 1 minus sine squared is the cosine squared. We know that the square root of the cosine squared is cosine. And we know that that cosine on the bottom is going to cancel with this cosine on top. So I'm going to do that. And now it's done. So really, this integral simplifies into the integral of sine squared theta d theta, which is why we spent a chunk of time in section 8.1 and another chunk of time in section 8.3 talking about the half angle formula. What we have as the result of this is still a composite function. We started doing substitutions up here because there was a lot of composite functions going on, and we still have that. This isn't just the sine, it's the sine and that thing is getting squared. So function composition is not safe. We have to use a special tool. We can't use substitution again because there's no other piece to match with the derivative of sine. So we have to use the half angle formula. The half angle formula for sine is sine squared theta is 1 minus cosine of 2 theta over 4. Sorry, over 2. The 4 is going to get involved later. So I will trig identity this into the integral of 1 minus the cosine of 2 theta over 2 d theta. I'll pull the 1/2 on the outside actually. 1/2 the integral of 1 minus cosine 2 theta d theta. The integral of 1, as usual, is theta. The integral of negative cosine 2 theta is negative sine 2 theta over 2. Let's also see at the end because this is indefinite. And so the result we get so far is 1/2 theta minus 1/4 the sine of 2 theta plus c. And it's very tempting to be like, that was a lot of work, I just integrated that and now I'm done. We're not done. The problem is about x's. We cannot have an answer. It's about thetas. So we need to substitute some thetas in here, and we'll see what that looks like. I'm going to give myself a little bit more space up here, because this is going to be sort of a lot to write. I thought I could not have to erase it. I skipped all these steps in the middle so I could not erase something, but alas. 1/2 theta is the arcsine of x minus 1/4 of the sine of two arcsines of x plus c. So now the question is, how do we simplify this? And the answer is you don't. Just leave it alone. I don't care about simplifying it. Put a box on it, call it a day, you're finished. No one wants to see that. I don't even know if there is a good simplification for this. The sine of twice the arcsine. Maybe there's some trig identity somewhere that cleans that up nicely, but I have no idea. Maybe a different form of some half angle formula for, or double angle formula for sine. It's probably out there somewhere. I just don't care. This is good enough for me. So that's sort of the last of like the weird nonsense we're going to see in the trig substitution section. Honestly, it's a pretty quick section. We'll do some very regular, pretty boring integrals that turn into arcsines, and we'll figure out how to deal with various numbers in various places. And then I think there's one or two like this where you'll get, instead of weird numbers popping up, you'll get weird x's popping up, and you'll have to deal with those. So remember that exactly one x, you do not need to deal with any of this Arctrig nonsense. You can do a regular inside-outside-other substitution technique. If there are 0 x's or 2 x's or a different number, any number of x's that isn't 1, then you got to go with this Arctrig stuff. Which is why this section is subtitled Arctrig. The trig substitution is about doing this and then turning your thetas into arcsines, and that's where all this happens. Two other things that we need to mention quickly before I cut this video. One of them is arc cosines. Remember when we did calculus, we said that the derivative of the arcsine of x is 1 over the square root of 1 minus x squared, and we said that the derivative of arc cosine of x, not theta, the derivative of the arc cosine of x is negative 1 over the square root of 1 minus x squared. They're basically exactly the same. So, if you see an integral with this in it, the weird bit is, we're not going to call that an arcsine. We're going to pull the negative 1 to the, or let me actually write the integral. If you see an integral of negative 1 over the square root of 1 minus x squared dx, it's tempting to be like, oh, I recognize that. That's the arc cosine. That's actually not what mathematical, convention has us do. When you see something like this, it is traditional to pull the negative 1 to the outside, just like you would any other coefficient up here, like we did with the 19. You pull the coefficient out, you have this thing, and that's the arcsine. It's negative 1 arcsine, but it's still just the arcsine plus c. So this is the weird thing. We can take a derivative of the arc cosine, but there really sort of isn't an integral that traditionally turns back into an arc cosine. This form just always turns into arcsines with various addition and subtraction things involved, which I think is pretty neat. It's an interesting little quirk of this. And the very last thing we need to say is about arctangents. Hopefully you remember the derivative of an arctangent. It looks kind of like this. So, if you're feeling very brave and you want to do some fun stuff, you can set x equal to the tangent of theta and substitute that in alongside its derivative dx, which is 1 over cosine squared d theta. you can substitute these guys in, you can do a lot of simplification and a lot of cleaning stuff up, and you should end up eventually with the integral of 1 d theta, which is theta, plus c, which is the arctan of x plus c. So, if you're feeling ambitious about all the steps, do the steps. I'm sure that it will be an extremely entertaining time. It's a good way to kill time during quarantine. Have fun. If you want to not go through all of that, and trust me that the integral of 1 over x squared plus 1 is the arctan, and that you could modify this with coefficients in interesting ways, you could just trust me and then we'll be all set. So, I'll leave the choice up to you, and I will end this video because my voice is right about done.